Welcome to Education Beyond Borders Nano Knowledge Lectures. I am Kayla, your digital educator. Today let us look at carbon bonds. In part 1 of the Molecules of Life Nano lecture, we learned about the 4 molecules that constitute the building blocks of life on planet Earth, namely hydrogen, oxygen, nitrogen, and carbon. The central molecule to this architecture is the carbon atom. There are 3 reasons why carbon was chosen by nature to become the central molecule in the backbone of life. The easy way to remember this is the first 3 letters of carbon's name. CAR, which stands for complexity, abundance, and robustness. C for complexity. The structural variety seen in biological molecules requires that the core atom chosen to form its scaffolding should be capable for a variety of bonds with a number of partner molecules. Carbon, with its capacity to form 4 covalent bonds with a wide variety of other atoms, provides the greatest bandwidth for the creation of complex structures. In the periodic table of elements, carbon forms the group with the capacity for the highest number of covalent bonds. Other members of the same periodic table group that can similarly form 4 bonds are silicon, germanium, tin, lead, and flavonium. So, while these 5 other elements in the same group have the same capacity for complex bond structure as carbon, we will see that they fail the test of matching the other 2 requirements of the CAR rule, namely abundance and robustness of bond structure. When we want to build a city with Lego bricks, then we are going to need an abundance of Lego bricks. Similarly, when we look at the 6 elements that are capable of forming complex bonds through the lens of their abundance on Earth, we see that only 2 elements are most abundant, namely carbon and silicon. The remaining 4 elements are nowhere as abundant on the planet. The last criteria is robustness of bond strength. In this, we see that carbon's outermost shell, which is the shell engaged in the forming of covalent bonds, is closest to its nucleus compared to silicon. Carbon's electrons are on its second shell, closer to the nucleus, whereas silicon has its unpaired electrons farther away from its nucleus, on its third shell. The consequence of this is that when silicon bonds with other atoms, including itself, the bonds formed are weaker and thus less stable. This bond strength factor is critical when choosing the atom that would serve as a backbone of biological compounds. Example hydrogen, oxygen, and nitrogen are also abundant in nature, but they have limited capacity for complex bond structures due to their being monovalent, divalent, or trivalent elements, and their bond strength is significantly lower than carbon. The backbone of a biological compound has to be strong enough to withstand the conditions under which other parts of the molecule break their bonds and react chemically with other atoms' molecules. So the carbon-carbon scaffold needs to remain intact while its functional components of its side chains can break apart. A molecular scaffold made from nitrogen or silicon would more easily break apart. For these reasons, carbon becomes the choice of nature to build the backbone of biological molecules under the conditions of temperature and pressure prevalent on Earth. Note that it is theoretically possible for another element, like silicon for example, to become the building block of life on another planet under conditions of temperature and pressure that make that element more suitable for that function. The essence of the vast variety and complexity of biological compounds is the variety of covalent bonds that can form between the 4 atoms of life, namely hydrogen, oxygen, nitrogen, and carbon. Therefore, before we can understand carbon bonds, we need to understand covalent bonds. A covalent bond is a chemical bond that involves the sharing of electrons to form electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs. The stable balance of attractive and repulsive forces between atoms when they share electrons is known as covalent bonding. For many molecules, the sharing of electrons allows each atom to attain the equivalent of a full valence shell, corresponding to a stable electronic configuration. In organic chemistry, covalent bonding is much more common than ionic bonding. In the figure shown here, the 2 hydrogen atoms of the hydrogen molecule share their 2 electrons via covalent bonding. Covalency is greatest between atoms of similar electronegativities. Thus, covalent bonding does not necessarily require that the 2 atoms be of the same elements, only that they be of comparable electronegativity. A carbon-carbon bond is a covalent bond between two carbon atoms. The most common form is the single bond. In chemistry, a single bond is a chemical bond between two atoms involving two valence electrons. That is, the atoms share one pair of electrons where the bond forms. Therefore, a single bond is a type of covalent bond. When shared, each of the two electrons involved is no longer in the sole possession of the orbital in which it originated. Rather, both of the two electrons spend time in either of the orbitals which overlap in the bonding process. This is shown in this figure. Now, carbon bonds may occur as single, double, or triple bonds. A double bond is a covalent bond between two atoms involving 4 bonding electrons as opposed to 2 in a single bond. Double bonds occur most commonly between two carbon atoms, for example in alkenes. Many double bonds exist between two different elements, for example, in a carbonyl group between a carbon atom and an oxygen atom. Other common double bonds are found in azo compounds, Nut equals sign N, imines, C equals sign N, and sulfoxides, S equals sign O. In a skeletal formula, a double bond is drawn as two parallel lines between the two connected atoms represented typographically as the equals sign. Double bonds involving carbon are stronger and shorter than single bonds. The bond order is 2. Double bonds are also electron-rich, which makes them potentially more reactive in the presence of a strong electron acceptor, such as a halogen atom like chlorine. A triple bond in chemistry is a chemical bond between two atoms involving 6 bonding electrons instead of the usual 2 in a covalent single bond. Triple bonds are stronger than the equivalent single bonds or double bonds, with a bond order of 3. The most common triple bond is in a nitrogen N2 molecule. The second most common is that between two carbon atoms, which can be found in alkynes. Other functional groups containing a triple bond are cyanides and isocyanides. Some diatomic molecules, such as diphosphorus and carbon monoxide, are also triple bonded. In skeletal formulae, the triple bond is drawn as 3 parallel lines between the two connected atoms. This concludes this nano knowledge lecture on molecules of life. Part 2, Carbon bonds. In the next lecture, we will focus on bond angles and bond strengths.